So anyway, like Fridays is game days, so let's do the calculus prayer. Father, Son, Holy Spirit, amen. This is the beginning of a new day. God has given me this day to use as I will. I can waste or use it for good. What I do today is important because I'm exchanging a day of my life for it. When tomorrow comes, today will be gone forever. Today is place something I have traded for it. I want to be gain, not loss, good, not evil, success, not failure, in order that I shall not regret the price I paid for it. The future is a whole string of nows. Amen. All right. So let's get going here. First of all, how did 2.2 go? So Jack, hopefully you figured out when they reference an example from the section, you got to go back into the, not into the problems, but into the reading there. Did you get that figured out okay?
Yeah, I got it.
Okay. So what, as a class, so I said 2.2 was due today. So what I'd like you to do sometime over the weekend is either today or over the weekend is scan me a PDF of it. But I will, since we're remote, I will answer any questions if there's any questions that you have. Was there any particular questions on 2.2? Take that as a no. You can use the chat too. So I'll assume there aren't any. So then you can tell me what you got for number 6C. Excuse me. We had to show continuity, but then what's number 6? What's the left-handed derivative? What'd you get? Could be easy to type it in the chat function too if you want. Okay, Hannah got 1. Anybody else agree? That was the left-handed derivative, right? Yeah, the left-handed derivative. Okay, what about the right-handed derivative? Somebody else. Hannah's done. Oh, Hannah, you're done. All right, perfect. All right. So Hannah, John, Carter, good job. So is it, since left and right-handed derivatives are not the same, we know it's not differentiable, right? Number 8, by the way, these are fairly easy to graph as well. I did include the graph, but anyway, continuity, I do prefer that you show those 3 bullet points at the point where they connect. So just besides the graph, make sure you're showing those 3 bullet points. If you didn't on part A or B or whatever that was, showing if it's continuous there. Anyways, so basically on number 6, what we noticed is that is continuous at that point, but not differentiable there. So continuity does not guarantee differentiability. We also notice that in the absolute value of x at x equals 0, that's not differentiable at 0 with that sharp point there. This is kind of a sharp point because it's 2 different styles of graphs connecting there, so it kind of makes a sharp edge there, so we can't balance the tangent line. But as video showed, if a function is differentiable, which means the derivative exists at that point, then we're guaranteed that it's going to be continuous. Anyway, and then number 8, what did somebody get for the left-handed derivative? Somebody else that hadn't answered yet. And Carter, you can answer for Luke. Unless that was Luke, then you got to answer for Carter. Number 8, C, left-handed derivative. Anyone? Bueller? Jack got 4. Okay, Jackson. What would you get for the right-handed derivative? You can either type it or say it. It might be easier to say it. Yep. Good job, Jordan. Infinity. So therefore, that's not differentiable at x sub 1 equals 2. Okay. Number 22, we're looking for, well, we got to come up with the equations of the graphs, right? And then there's a lot of looking at the left and right-handed derivatives there. So compare with each other on that. Maybe I'll give you time at the end to compare your answers on 22 and 32, and instead of going through that. But sounds like nobody has any questions for me at all on 2.1 or 2.2. Is that correct? If not, let me know, or forever hold your "Let there be peace on earth." All right. Number section 2.4. So now we're gonna start getting into specific derivatives here, like theorems, proven facts, which is kind of nice. So hopefully you've seen videos on this, but we'll just kind of go through them pretty quick and try and do some examples. So once again, we're skipping section 2.3, so hopefully you can see the whiteboard, and hopefully you can see me right in section 2.4 here. Okay, if not, somebody needs to let me know. So you shouldn't be able to see me anymore. All right, a couple of theorems that we have. If we have some proven facts, some specific theorems, if we have if f of x equals some constant, then the derivative of f at any point x is actually going to equal 0. And why would that be? So this is a fairly simple deal. If we have the xy axis or x f of x, and if f of x is a constant height, so it's the same height of k here, basically what would the tangent line be? So if I put a tangent line against that, what would the slope of the tangent line? Is the derivative is the slope of the tangent line at any point x, right? So the slope of a flat line would be 0, correct? So the derivative of a constant is 0. So that's how I remember that theorem. Let's look at another one. So that's one theorem. If I've got the derivative, if f of x is some constant times a function, and I want the derivative of that, then f prime at x is going to be the constant times the derivative of the function. Okay, and so I'll give you an example of that later. So here's another theorem that we have. The derivative of a constant times a function is the constant times the derivative of the function. So we can essentially pull that constant out front. I'm going to give you another one here. If I have f of x equals x to a power, so let n be some real number, basically what I can say then is f prime at x, the derivative of f evaluated at x. Really what we can do is think of it this way. The way I like to think of it is drop that n down in front and then reduce the exponent by 1. So it's going to be n times x to the n minus 1 power. So this was what I kind of showed you before. If we had, for example, if I have f of x equals x to the 4th power, then the derivative of f prime at x, is going to equal 4x to the 3rd power. So we have a very quick and easy way to come up with the derivative using a theorem or a proven fact. So if I'm asking to come up with the derivative or the slope of the tangent line, the derivative by the definition, then it's going to be that difference quotient. The limit as delta x approaches 0. The difference quotient, unless you'd use the alternate version of that. But if we're just looking for what the derivative is, then we can use these theorems as well. So all of a sudden, life gets a lot easier. Some of these are proven in your book. Some of these are proven in my videos. But anyway, this is going to be the slope of the tangent line at any point x. Okay. So, for example, continue that. If I have g of x equals the square root of x. We did the derivative of this before, but really what I can do is I can rewrite that as a power. So I could use the power rule. That's the last term I have, is actually called the power rule for derivatives. I could write that as x to the 1/2 power. If I do that, and that implies that g prime at x is going to be 1/2 x to the 1/2 minus 1 power, which ends up being 1/2 x to the minus 1 power. So 1 minus 1/2 is minus 1/2. Now, we know if you have a negative exponent, we could drop it in the denominator and make it positive. So this ends up being 1 over 2x to the 1/2 power. Then what we want is we want math etiquette. So if you notice, the original function here had a square root in it. So what I want is I want my final answer to have a square root in it. So this is going to be 1 over 2 times the square root of x. And so I believe we did the square root derivative one of the last 2 class periods. We got 1 over 2 square root of x. But anyway, so this is a much easier way to come up with that very quickly. Now, of course, derivative doesn't exist. What's the domain of g prime? Derivative. The domain of the derivative is not including 0 to including infinity or positive reals, right? So it is the domain of that is the positive reals, because I cannot plug in 0 in the denominator. So even though the domain of g is all reals including 0, right? Positive reals including 0, the g prime does not have the same domain here because you would be dividing by 0. So we got to be a little bit cautious on that and go from there. Now, we did talk about the right-handed derivative of the square root of x. We did have a derivative from the right, and it was positive infinity. But basically what happens when you're dividing by something getting close to 0, it explodes. So the right-handed derivative was positive infinity there for the square root of x. We did that yesterday. So let's look at one more on the examples here. If I have, change colors here. If I've got h of x equals 2 times the cubed root of x to the 4th power, x cubed root of x squared. Let's do this one. Really what I want to do is I want to rewrite this as 2 times x to a power. So the exponent is in the numerator and the root is in the denominator. So when you have, if I have the nth root of x to the nth power, we just need to remember the algebra rule. That's x to the m divided by n power. Now I could rewrite this a different way. I could call that nth root of x quantity to the nth power. I could do it like that too, but notice n is your root in this case, and m is your power or your exponent. So the power is on top. So anyway, h of x I could rewrite as 2 times x to the 2/3 power. And then if I want the derivative of h with respect to x, basically the derivative of a constant times a function is the constant times the derivative of the function. Okay, so basically it's 2 times x to the 2/3 prime is one way to write that. I'm going to show you some different ways to write it. But anyway, this ends up equaling 2 times, and then I take that, drop it down in front, so it's 2/3 x to the 1 minus 2/3, which ends up being minus 1/3, and then we use math etiquette here. So this equals 4/3 when you multiply constants together. That's 4/3, and then x to the minus 1/3. So once again, in math etiquette, because I had a root in the original problem, I want a root in my answer. So it's going to end up being 4 over 3 times the cubed root of x. So that's going to end up being the derivative there. So I'm going to do a quick pause here before I get into some notations. Once again, I know I talked through these on the videos, but I'm going to start using them here. Any questions on any of these theorems that I've done so far? Take that as a no. All right. So I do want to say, if I have for notation for a derivative, basically we have slope of the tangent line at any point x for a function f of x. Let f of x be a function. Okay, so we've got f of x. The slope of the tangent line is f prime at x, or we can also say the derivative of f evaluated at x. So another way that we can write that is df dx. So we can write it as kind of a quotient here. We say df dx for the derivative of f with respect to x. Now notice if f of x is y, then how else could we write that? So the slope of the tangent line at any point x is going to be, instead of f prime, we could also call it y prime, right? And then what else could we call that? We could call it the derivative of y with respect to x. So dy dx is another way that really means the same thing if y is a function. Now, what is this like? This is a lot like delta y over delta x. And if you remember, what is delta y over delta x? So d for delta, right? This is a small d, so what's the difference? The difference is this is a bigger, if I've got my graph, I've got a bigger distance between points. So if this is my point x that I'm approaching, really what I have is I've got delta y here, delta x here, and this is the slope of the secant line, right? So delta y over delta x is the slope of the secant line. So then what did we do? Then what we did is we took the limit as delta x approached 0. So we let the denominator get closer and closer and closer to 0. So then I'd get closer and closer and closer to 0 here, right? And then eventually be on the tangent line there. So the big difference between a delta y and a little dy is a little d is really considered to be infinitesimal change in that distance. In other words, it's super small, super close. Where delta could be pretty big. I mean, we could be at 1 or 10 or 100 units away for a delta, right? Where a dy, we're talking, 1 millionth, 1 trillionth. You're getting super close, super tiny. So that's kind of the intrinsical difference between a dy dx, tiny change in y over a tiny change in x. So you're not very far away at all. So you're essentially on that tangent line, where a delta y over delta x is kind of a bigger change, and that's actually gives you the slope of the secant line, either to the right, or of course it could be, to the left over here as well on that. So there are a couple different notations. Now, just to keep going with that fact, we could also say the derivative of f with respect to x. So I could use a capital D instead of putting df dx. I could put capital D, the derivative of f with respect to x, and I can put the variable that you're taking it with to in the denominator. Most of our functions are in terms of x because of graphing, so we're almost always taking the derivative with respect to x, but there are other variables out there. So for example, if I had if I have g equals y to the 10th power, then if I have the derivative of g with respect to y, I have the derivative of g with respect to y, then basically y is my variable. So I act like I use the power rule for that. So it'd be 10y to the 9th. Now y in itself might be a function of x, so we're going to get into some other things there. So if I had the derivative of g with respect to x and y is some other function of x, that's a composition function. So we're not quite ready for that yet. Okay, so a couple other theorems here. If we have the sum of functions, so if I have the derivative with respect to x, oh, by the way, here's another way to write it. The derivative with respect to x of f of x, right? But if I have the derivative of the sum of functions, then that's going to be the derivative of the first one, which I'm going to write f prime at x, plus the derivative of the second one, g prime at x. Now, that doesn't really match the notation I used on top, so I could have this as df dx, the derivative of f with respect to x, plus the derivative of g with respect to x. Long story short, the derivative of the sum of functions is the sum of the derivatives. So I say the derivative of the sum is the sum of the derivatives. By the way, we also have that for the derivative of the difference, meaning the derivative of the difference between two functions is going to be the difference of the derivatives. Okay, so let's look at an example of this. If I have h of x equals x cubed minus 3x squared plus 4, and I want h prime at x. Well, this is, by the way, this generalizes when we have multiple functions. So I can just say, I can take the derivative of each part. This is the sum and difference of functions. What I can do is I can say, hey, I can take the derivative of this part, which is 3x squared, using the power rule, minus the derivative of the next part, which derivative of 3x squared is what? Well, the derivative of constant times a function is the constant 3 times the derivative of x squared would be 2x to the first. So 3 times 2x is actually 6x. So the way I think about that is I'm going to drop that down in front. If there's a number there, I multiply it when I drop it down. That's how I think of it. And then, of course, that reduces by 1. And then plus what? Well, what's the derivative of 4? 0, right? So that really doesn't factor into my answer there. So the derivative of constant is 0. A couple other theorems. If I have y equals mx plus b, so I have a line. Well, we should know what the derivative is, right? So here's your line, y equals mx plus b. If I set a tangent line on that, the slope of the tangent line is going to be the same as the slope of the line, right? So the slope of the tangent line is actually going to equal m. The slope of the line is going to be the same. So the reality is if I have y equals mx plus b, then y prime is going to equal m. Now, what's y prime? Y prime is the derivative of y with respect to x. It's also the slope of the tangent line at any point x, right? So if we have a line y equals mx plus b, the derivative or instantaneous rate of change is m. So example, if I have y equals 4x minus 3, then what's y prime? Y prime is going to equal 4, right? Now, we could also use the derivative of the differences of the difference of the derivatives. If I do that, the derivative of 4x is a constant times a function, right? So if I take that 1, drop it down, use the power rule, 1 times 4 is 4, x to the 0 power. So I could write that as 4x to the 0 power, and then minus the derivative of constant is 0, right? But x to the 0 power is what? X to the 0 power equals 1 if x does not equal 0. So if x does not equal 0, anything to the 0 power is 1. So I to the 0 power is what? It's 1. But 0 to the 0 power, so this is for Isaac who's not here today, 0 to the 0 power is actually indeterminate. Much like 0 divided by 0, it's an indeterminate form. So be careful on that one. But as long as you're away from 0 there. So anyway, long story short, going to be a lot easier if we have a line. The derivative of a line is its slope. Okay? All right. So trying to see what else we have. So then we have the product rule. So the ones that are a little bit more involved or different than what you might expect would be the product rule and the quotient rule, and then the composition of functions, which leads to the chain rule. Anyway, if I go to the product rule, product means multiply, right? So if I have f times g evaluated at x, and I want the derivative of that, so d dx of that, or I could just put a prime on it. So the derivative of a product of functions, remember by definition, this is the derivative with respect to x of f of x times g of x, right? So section 1.1, we looked at the product of functions. F times g evaluated at x is defined to be f of x times g of x, right? Well, what I have here is I have a first one and a second one. So this is how I remember it. So it's the first one times the derivative of the second one plus the second one times the derivative of the first one. So this is not, do not just multiply the derivatives together, because that's not going to be okay most of the time. Every once in a while when you get zeros in there, it works out, but it's not the theorem. The theorem is the derivative of a product is the first function times the derivative of the second function plus the second function times the derivative of the first. And notice that I'm saying the words as I do it, so make sure that you say the words as you do it as well. So let's look at an example of this. If I look at an example and I have, well, I'm gonna just give myself some room here. So let's say I've got h of x equals 3x squared minus 2 times 4x to the 10th power minus 3x cubed. Okay, we're just gonna keep it fairly simple like that. One of the ways this is a product of functions, right? By the way, any polynomial has a derivative, which is nice. But anyway, so what's h prime at x? Well, h prime at x is going to be the first one, 3x squared minus 2, so that didn't change at all, times the derivative of the second one. The derivative of the second one, derivative of the difference is the difference of the derivatives. So 10, and then derivative of a constant times a function is the constant times the derivative of the function. So 4 times the derivative of x to the 10th. Take that 10, drop it down. That's 40x to the 9th. And then minus the derivative of the second one, constant times the function. And then the power rule, dropping that 3 down in front, gives me 9x to the 2nd. So this is the derivative of the second one, right? But then the theorem says first times the derivative of the second plus the second one, which is 4x 10th minus 3x cubed. Notice that didn't change at all, times the derivative of the first one. So now the derivative of the first one is 6x to the first, and then minus 0, or basically just times 6x. Right? So this, unless I tell you to simplify it, is good enough for the answer. It's not in simplest form. It will not agree with the answers in the back of the book, because the back of the book is going to multiply all that out and come up with an equivalent answer. So the other way that we could have done this is we could have actually multiplied this out together, FOILed this out originally. I could have took 3x squared times each part, and then minus 2 times each part, right? And then taken the derivative. And so if I would have done that, what would I get there? I would 3x squared times 4x to the 10th is 12, and then we got to add exponents, right? X to the 12th, and then minus 9x to the 5th, and then minus 2 times all that would be minus 8x to the 10th, plus, minus is plus 6x cubed, right? So this is equivalent to h of x, right? So h equals, h of x equals that, which implies that h prime would be the derivative of this thing, which derivative of the sum and difference of functions is the sum and difference derivatives. So we just take the derivative of each part. Of course, 12 squared is a gross, which is 144 x to the 11th, and then minus 45 x to the 4th, and then minus 80 x to the 9th, and then plus 18 x squared, taking the derivative of each part. So this may be what the back of the book has, but I don't really want multiplying that out when we can just use the theorem. Now, assuming I did all that correct, if I multiplied these things out, multiplied this times each part, and then minus 2 times each part, and then 6x times 4x to the 10th, and then times minus 3x cubed. If I multiply all this out for my final answer, I'm going to end up being equivalent to this answer down here as well. Once again, it's not a matter of, in this case, we're trying to learn the theorem, so it's not necessarily trying to do it the easiest, but we're trying to avoid algebraic simplification. We know that we can do that, but we certainly don't have to do it all the time. We can use the theorems when appropriate. By the way, I want to go back. I want to back up so I don't forget it, and show you another example using. Let's just say I have P of X is I over 4x x to the fourth power. What if I have something like this? Well, I'm going to be a little bit careful. So that x to the fourth is in the denominator. So what I'd like to do is I'd like to write this as pi over 4 times x to the minus fourth power, and then take the derivative of it. So then dp dx is another way to write the derivative, or p prime would be multiply that minus 4 down in front. The 4's cancel, and I'll be left with minus pi, right? Then notice here it's x to the minus fourth. So it's going to be x to the minus fourth minus 1. So this ends up being minus pi x to the minus fifth, right? So the power of x goes left 1 unit, and we were at minus 4, so going left takes you to minus 5. And of course, that's not how we would write our final answer because of math etiquette. Our original problem had a positive component in the denominator, so we're going to write this as minus pi over x to the fifth power. So that's going to be the derivative. Now, I do want to show you the difference between pi over 4x to the fourth, and then I'm going to use a different function here. I'm going to call it h of x. If I have pi over 4x to the fourth power, in this case, the x to the fourth is not in the denominator. This is actually attached by multiplication. So this is simply a constant, k, times a function, f of x equals x to the fourth, where we can use the rule. So dh dx, or if you prefer h prime at x, in this case, would be the constant times the derivative of the function. So it would be pi over 4 times the derivative of x to the fourth. Our rule, drop that 4 down, 4x to the 1 less than that, 4x cubed. Then we got those 4's cancel out, and we end up with pi x cubed. So it is important to pay attention to your algebra rules, positive exponents, you know, all that type of stuff as you go here, etc., to do some of these. So the last thing I'm going to cover today, I think, as I'm running out of time, is a quotient rule. Let's look at this real quick. So the quotient rule says if I have numerator function divided by the denominator function, where the denominator does not equal to 0, right? Then if I want the derivative of this with respect to x, so derivative of that thing with respect to x, the derivative of the quotient is going to be, here's how I think of it. Bottom one times the derivative of the top minus the top times the derivative of the bottom, all over the bottom one squared. So it's going to be the bottom one times the derivative of the top, n prime, minus the top, n, times the derivative of the bottom. So in this case, denominator prime, all over the bottom one squared. Okay, so it ends up being this. So once again, it's probably easiest to remember this by words. A derivative of a quotient function is bottom times derivative of the top. So I start at the bottom. Bottom times derivative of the top minus the top times derivative of the bottom one, all over the bottom one squared. Notice it's a minus when it's a quotient, where it was a plus sign with the product. So I'm going to do one example real quick. If you got to get going, that's fine. I'll keep it on the recording. 2.4 is due Monday. We're going to do the same deal. Ask me any questions over the weekend. I expect to have everything but a couple questions done on it. So trying to have it ready to turn in, but definitely odd exercises are okay to ask. So if I have f of x equals 3x cubed minus 4x all over 2x plus 3, I have this, then f prime, the derivative, would be first times the, excuse me, No. The quotient rule. Bottom times the derivative of the top. So it'd be 2x plus 3 times the derivative of the top one, which is 9x squared minus 4, minus the top one, which is 3x cubed minus 4x, times the derivative of the bottom one, which is 2, all over the bottom one squared. So 2x plus 3 quantity squared. And then we can multiply that out on top, see if anything cancels. But if you don't need to simplify, we're good to go there. All right, thanks. Have a great weekend. Talk to you later.